Yeah, hello everyone. So this is a question from JEE Mains 2026 28 Jan evening, and the question is the correct order of acidic strength of the major products formed in the given reactions is. So there are some reactions given to us. So our first aim should be to know what is A, what is B, what is C and D, and then ultimately arrange them in the order of their acidic strength. Okay, so let's look at these reactions in detail. Yeah, so the first one. So first one, as we can say, PHNH2. So PHNH2 is nothing but aniline. And let's look at the reagent. So we have NaNO2 plus HCl. So, and also the temperature is less than 5 degrees Celsius. So these reagents are used whenever we have to do diazotization. Okay, so NaNO2 plus HCl. So these guys will convert this primary aromatic amine into a diazonium salt. So that process is known as diazotization. Okay, and also just some extra information, why do we need to have the temperature less than 5 degrees Celsius? It's because otherwise, instead of getting diazonium salts, we will be getting phenols. We don't want that. That's why it's important to keep the temperature below 5 degrees Celsius. Okay, so when we do the first step to A, the primary aromatic amine gets converted into a diazonium salt, and it looks like this. Okay, and in detail the structure is this is the structure. Okay, and this is known as benzene diazonium chloride, and obviously we get water as one of the side product. Okay, so when we in reaction A, when we did step 1, we got benzene diazonium chloride. Okay, let's see what are they doing in step 2. In step 2, they're reacting it with CuCN. Okay, so we are reacting benzene diazonium chloride with CuCN. So whenever we have benzene diazonium chloride reacting with CuCN dissolved in KCN, this reaction is known as Sandmeyer's reaction, and ultimately we get benzonitrile, that is benzene ring. I mean the diazonium group got substituted by the cyanide group, so we got, yeah, so this, and also nitrogen gas out. Okay, this is known as benzonitrile. Cool, so we got benzonitrile, and then we have a third step. The third step is acidic hydrolysis and heat. So when we do acidic hydrolysis and heat to a CN group, we know that it gets converted into a carboxylic acid. So therefore in the end we will be getting benzoic acid as our answer. Okay, so A is nothing but benzoic acid. Okay, so I will draw the structure here. So this is A. So let's talk about B. So B starting compound is propanol. Okay, so we have propanol. Okay, let's look at the reagent. The reagent is very interesting. If you see, this is Tollens reagent, ammoniacal silver nitrate solution. If you see Tollens reagent, and Tollens reagent is a very weak oxidizing agent. That's why it can act with aldehydes. Aldehydes can be converted into carboxylic acid by weak oxidizing agents also. So therefore, this Tollens reagent will convert the aldehyde into carboxylic acid having the same number of carbon atoms. So there are 1, 2, 3. So we will get a carboxylic acid containing 3 carbon atom, which is, so I will draw the structure CH3, CH2, COOH, propanoic acid. Okay, cool. Then let's look at reaction C. So we have methane and we have oxygen, and also so step one, so let's write it down. So we got this as CH3 CH2 COOH. Third one, C. So we have methane, mixture of methane and oxygen. So first is in the presence of molybdenum oxide, and also there should be heat and pressure. So we know that, so from the chapter hydrocarbons we know this, whenever we take a mixture of methane and oxygen in high pressure and heat and also molybdenum oxide, we always get the corresponding, or having one carbon atom aldehyde, which is methanol, HCHO, and also water as the side product. Cool. Now let us look at what is happening. What's the second step in C? The second step is we are taking Na2Cr2O7, sodium dichromate. If you remember, potassium dichromate is a very strong oxidizing agent. Same applies to sodium dichromate too. Okay, so it is also a very strong oxidizing agent. So therefore this HCHO in the presence of Na2Cr2O7 will be converted into the corresponding carboxylic acid having one carbon atom. So we will get HCOOH. So we are getting methanoic acid. So C is methanoic acid. Okay. And the fourth one we have a Grignard reagent, if you can see. And Grignard reagent reacting with CO2, obviously there should be dry ether since we have Grignard reagent, and we have acidic hydrolysis again. So let's see how does a Grignard reagent react with carbon dioxide. So I hope, so let's see the general reaction first. Plus C double bond O double bond O. So we write it in this fashion to understand. Okay, so negative charge, positive charge, oxygen takes these electrons because it is more electronegative. Here also magnesium being a metal, positive charge, negative charge. So therefore this part of the molecule goes and attacks this C. That's how the reaction proceeds. Okay, so here we have the Grignard reagent. The Grignard reagent is this CH2 MgBr and CO2. So positive, negative, positive, negative. So this part of the molecule is going there, and this part of the molecule is going here. So we will get, obviously C double bond O will be as it is. This C double bond O is as it is, and then this group comes and get attached here. So we will get CH2 and benzene ring. Okay, and also can you see this double bond will become a single bond because the pi bonds are becoming a lone pair there. So this becomes a single bond, and then MgBr goes and gets attached to this oxygen. So OMgBr. This is known as the addition product or adduct. Okay, now next is the acidic hydrolysis, H plus H2O, or you can simply write H3O plus. Okay, so whenever acidic hydrolysis happens, so the adduct gets converted into the corresponding carboxylic acid. So we will get the corresponding carboxylic acid. So we get this CH2, C double bond O and OH, and this part becomes plus MgOH Br. Okay, so this is known as phenyl acetic acid. Phenyl acetic acid. So therefore we have found out what are all the carboxylic acid that we need to compare their acidity. CH2, C double bond O, H. Okay, so these are A, B, C, D. So let's write them down, separately so that we can compare them. Okay, so A is benzoic acid, B is propanoic acid, C is Yeah, so this is B and C is HCOOH and D is phenyl acetic acid, CH2COOH. Okay, so now we have to compare the acidic strength of these guys. So before we do that, we need to talk about how to decide that which one is more acidic, which one is going to be less acidic. So always remember, carboxylic acids are the strongest, are one of the strongest highly acidic organic compounds. Okay, so I can represent them like this, and let's say we have a group here. Okay, so let's say I'm representing it as X. So we want these, if you want this carboxylic acid to be acidic, we want this guy to pull these electrons, so that oxygen, it becomes devoid of electrons. It wants, since we are pulling these electrons, this oxygen will get a positive charge, because of which it will try to gain these electrons towards itself, and then hence we can lose this hydrogen easily. So therefore we want X to be a electron withdrawing group. In that case, what's gonna happen? The electron density in OH bond is going to decrease, due to which, so the electron density in this bond, because since it's an electron withdrawing group, so it is withdrawing electrons, so therefore oxygen will be devoid of electrons, and hence it will try to pull these towards itself, and hence it will be easy to lose this hydrogen in the form of H plus. Okay, on the contrary, if you have a electron donating group, so what's that guy gonna do? So if you have electron donating group, so that guy is going to donate electrons. So since it is donating electrons, oxygen doesn't feel the necessity to pull these electrons towards itself, and hence it will be tough to break this bond. This does not happen. So therefore electron donating groups increase the electron density in OH bond, and therefore release of H plus ions is difficult. So we just need to know that electron withdrawing groups increase acidity, electron donating groups decrease acidity. Okay, cool. So if we look at all the four options, here we have a benzene ring. So benzene ring has plus R effect. Okay, that is electron donating resonance effect, and also we have minus I, which we are going to discuss how, because of electronegativity difference. B has only plus I effect, that is electron donating inductive effect. C does not contain any alkyl group. It does not have any alkyl group. So if you can see here, HC double bond O, OH. So there is no alkyl group to exert any effect. So therefore it is the strongest acid out of all the four that is given to us. Okay, so therefore C is the strongest. Okay, let's look at B. If we look at B, yes, as I wrote here, so I will write it again. B is CH3 CH2 COOH, right? So we can see here that this guy has only plus I effect, because this is a electron withdrawing R group, alkyl group, and it has electron donating effect, plus I effect. So therefore it increases the electron density in the OH bond, it increases electron density here, and hence it is the least acidic out of all the four. Okay, now let's look at A. So A is benzene ring, and we have C double bond O, and we have OH. Okay, so yeah, so when we talk about A, benzoic acid, we can clearly see that there is plus R effect. Plus R is that benzene can donate electrons to the system. Because of this, since it's a electron donating system, it's going to donate electrons to the system, so therefore it should lead to decrease in acidity. But to our surprise, this is quite acidic. Okay, So that's because there is something called minus I effect is also operating here, and that minus I effect is due to the electronegativity difference. So here we have a benzene ring and we have a sp2 carbon here, and this sp2 carbon is more electronegative, so therefore it pulls electron towards itself, and hence it decreases the electron density in the OH bond. Okay, so it decreases the electron density in this bond, and hence we can lose this hydrogen easily. Now one more thing that we need, so there are two effects going on, one is plus R and one is minus I. Okay, and I said that inductive effect is more dominant here. So the reason is, if you look at what happens to the carboxylate anion after losing the H plus, that is, it is, if we draw the resonance structures, so it will be like this, or you can represent it like this also. So yeah, we can represent it in the two resonance structure, and both are equivalent resonance structure, or the hybrid can be represented like this. This is how you represent the hybrid. Okay, now whenever we consider the cases of carboxylic acids, they are special. Conjugation of COO minus, this conjugation, okay, is so strong in itself that its conjugation with the rest of the compound, that these conjugation is very, very weak. So therefore the inductive effect dominates. So therefore whenever you have carboxylic acids, always remember that inductive effect is going to dominate over the resonance effect, because the conjugation here is so strong that the conjugation in the rest of the molecule is kind of ineffective. Okay, so the sp2 hybridized carbon, as we have it here, the sp2 hybridized carbon, so it reduces the electron density on carbonyl carbon, but still there is some amount of effect, plus R. Obviously we cannot neglect it, obviously minus I dominates, but there is still some plus I effect to make it less acidic than HCOOH. It is still less acidic than HCOOH because of this little amount of plus R effect. Okay, so therefore the order is obviously C will be more than A. C is HCOOH. HCOOH has no such effects like plus R, but A has plus R and minus I. Obviously minus I dominates, but there is some amount of plus R due to which C is more than A. And in the last case, we have which one is left? One second. Yes, so we have D left. D is phenylacetic acid. So when we look at phenylacetic acid, so this is our phenylacetic acid, and CH2 C double bond OOH. Now one thing is, there is going to be no resonance at all, because double, single, single, so there is no conjugation, no scope for conjugation. So there is only minus I effect, that is, we have sp2 carbon here, this guy is gonna pull the electron towards itself. But there is a problem. Okay, the problem is that it is at a distance now compared to this carbon. So this electronegative, this inductive effect is going to be weaker compared to the previous case, compared to the case of benzoic acid, because it's at a distance. This electronegative carbon is at a distance now, so therefore so it has a weak minus I compared to benzoic acid, so therefore the electron withdrawing ability will be a bit less. So therefore maximum is C, no doubt at all, that is HCOOH, because there are no such plus R effect. Then we have A. A is benzoic acid. Benzoic acid has plus R, but also it has a very dominant minus I, and that minus I is this carbon is near, you can see. Then we will have D. D is phenylacetic acid. Phenylacetic acid is CH2 COOH. Now here you can see this is the sp2 carbon. It is at a distance compared to the OH bond, so therefore it is lesser than A. And in the last we will have B. B is our propanoic acid, CH3 CH2 COOH. As you can see, there is only plus I effect, electron donating to the system, so therefore OH bond, it's tough to break that, so therefore B has the least acidic strength. So the order is C, A, D and B. Yeah, thank you.